Now, I always like to get into it as quickly as possible, so here is your first RISC-V instruction. NOP, or no op, no operation, no registers, no values, no nothing. A no-op is generally just there in code to pad or align bytes to make them go on some particular byte boundary, for instance, multiples of 2, multiples of 4, multiples of 16, and so forth. And sometimes on some architectures, it's there to delay time, but that's not how it's used on this architecture. Now, to introduce you to the conventions I'll be using every time I introduce a new assembly instruction, we'll collect a nice little star here, and then I'll also indicate which ISA it is part of. In this case, I say RV32I. But I want you to remember that RV32I instructions are actually included in the RV64I base ISA. So anytime I put RV32I, don't think that it is exclusively only available for 32-bit code. It will also be available for RV64I ISA compiled code, as will be used in this class. But I've got some news for you, some NOP news. NOP is not a real instruction. It's a pseudo instruction, or instruction alias. Pseudo instructions walk among us. Open your eyes, sheeple! So, in this class, I'm going to be using the convention of referencing the 1984 series V for visitors. So I've never actually seen this series, but my wife has, and she said that it gave her nightmares as a kid. So the basic premise of the series is that some aliens come and they look like humans, but beneath their skin, they're actually reptiles who are not particularly friendly, but they try to act like they're friendly. Ironically enough, I think this is where the actual real conspiracy theory that there are actual elites in power in the world are actually reptiles beneath their skin. I feel like it's a not particularly creative, reappropriation of the conspiracy from this particular TV show. Anyway, so every time we encounter a pseudo instruction, we will have some V creatures. So behind the scenes, whenever you see a disassembler showing you a NOP, or if you put into an assembler, hey, I would like to use a NOP, most of the time what it's actually going to be using is the add-I assembly instruction with add-I x0, x0, and 0. There are many different sequences that can do nothing, but this is sort of the recommended version. So before we get into what that add-I is, I want to introduce some conventions I'm going to be using for writing assembly instructions. So if you see something like italic RD, that is a destination general purpose register. If you see RS, that is a source general purpose register if the particular assembly instruction takes only a single source. On the other hand, if it takes multiple source registers, you will have an RS1 for the first source register and RS2 for the second general purpose source register. And I explicitly call out that all of these are general purpose registers, meaning that you cannot use the PC or program counter register for assembly instructions that have these indications. We also see things like IMM for immediate and N for an N-bit signed immediate in this case. So if I say IMM N, it's going to mean, for instance, IMM 12, that is a signed 12-bit immediate. It's going to be sign extended up to whatever the X-lang size is when it's ultimately used, be it 32, 64, 128 bits. There's only going to be a couple of exceptions to this later on when we talk about shift instructions. So most of the time, anytime you see me saying IMM 12, for instance, say it's a 12-bit signed immediate. And immediate is, again, just a special word for a constant that is baked into an assembly stream. If you see U, IMM N, that means it is a unsigned N-bit immediate. So that's not going to be sign extended, it's going to be 0 extended. You'll actually see throughout the assembly instructions that the bias is very much to always be using signed stuff, and usually if they're going to use unsigned, it's going to be a separate assembly instruction that will have a U somewhere in its name to indicate, hey, by the way, this is the unsigned version of this assembly instruction, and consequently you'll also see unsigned immediates used in the notation. There's a small modification of that. There's the NZ for non-zero signed. We could also have an NZU IMM. I don't remember for sure if we see any of those in this class, but basically that would be non-zero unsigned version of this. So again, an immediate, it's n bits long, and in this case, it is specifically saying it shall not be equal to 0. It is reserved or otherwise unacceptable for it to be 0. And then the final form has an uppercase U to indicate that it is setting the upper n bits of an immediate. So most commonly, this is going to be the upper 20 bits to go along with the other things doing the lower 12 bits. And so upper 20 plus lower 12 equals a 32-bit immediate. But this can be upper n, it could be 17, it could be some other value. And so the U, capital U, indicates it's setting the upper bits, not just the lower bits. So RISC-V immediates, again, immediate is just a constant value that is hard-coded into the assembly instruction. It's just a special name for that type of constant. And in RISC-V, if you see assembly instructions that end in an I, that is usually indicating that it's a form that takes an immediate. So add I is not adding two registers together, it's adding a register to an immediate. Now immediates, if they're n-bit, most commonly 12-bit, they're going to be signed values that are sign extended to xlang bits, be it 32, 64, 128, before they're actually used. So the possible 12-bit values are from 0 up to FFF. And those as signed values would be 0, 1, and then all the way up to the maximum positive value, which is 7FF, which is 2047. And the negative values are -1, which is FFF, all the way to -2048, which is 800. So that's our possible values for 12 bits. And again, those would be sign extended up. So if it was FFF, 3 Fs, it would be sign extended to 8 Fs if it was a 32-bit value. So I want to give you a little bit of an intuition behind why things like 12-bit immediates are very common in RISC-V assembly instructions. So we start with the premise that the assembly instructions themselves for RV32I and 64I are going to be encoded in 32 bits. And if it's compressed, then it's going to be 16 bits. So that means you have a very small number of bits in which to encode actual immediates. So they don't have any notion of like 32 bits for the assembly instruction and then another 32 bits for the immediate. The immediates are actually encoded directly into 32 bits for the assembly instruction. So I don't want to get into all the nitty-gritty details about assembly instruction encoding, just to say that the bits are broken up in very specific ways. And if we looked at the actual details, we would see that for add I, for instance, the 12-bit immediate that it can take, the 12-bit signed immediate, is encoded in bits 20 through 31. So basically they set aside these 12 bits and they say these are going to be the 12-bit values 0 through FFF that are available for use in this add I assembly instruction. So it's very often 12 bits, it's very often smaller than that for the compressed versions, but this just is to give you a little bit of an intuition of why you can't just have, 32-bit immediates. It's because everything is all encoded in the 32-bit assembly instruction itself. So back to the lies I tell. Don't trust me. I said NOP was your first assembly instruction, but it's actually an insidious pseudo instruction. So what is the actual instruction that backs it? It is add I. This is the add immediate to register. This is our first real assembly instruction. Add I has a destination register here, a source register, and a 12-bit signed immediate. So what operation does this do? It takes the RS, the source register, adds the sign extended 12-bit immediate, and places the result in the destination register. So for instance, for NOP, we said that that is actually encoded by add I x0, x0, 0. And so that means you're taking the 0 register, x0, the mnemonic for that is 0 register. The 0 register, which is always hard-coded to 0, read from that, get a 0, add 0, store it back into the 0 register, but of course no writes to the 0 register ever make any difference because the 0 register is hard-coded to 0. So that's a whole bunch of no actual real operation occurring. Now, one miscellaneous thing that I want to say is that the immediate 12s, even though they're signed numbers, but they will always be shown in decimal in GDB as we debug things. As of right now, there doesn't appear to be any way to configure it to display in hex. So for instance, here's some other examples. We could have add I x1, x2, 1337. What is that doing? It's doing this is the source, x2 plus, so whatever the value is stored in x2 plus 1337, and store the result back into the destination register x1. This is an okay assembly instruction because 1337 can be encoded within the 12-bit range. We could have an alternative, add I SP SP -48. This is also okay because -48 was within that 12-bit range. So stack pointer minus 48 or plus -48 and store the result back into the stack pointer. This assembly instruction, on the other hand, is not an actual valid assembly instruction. You could not encode this. You could not put this into the assembly stream because you cannot encode the immediate 31337 into 12 bits. It's just beyond the range. The maximum positive value was 2047. So this is all the nitty-gritty details that the manual has about how all of the general purpose RV32I base ISA instructions are. But again, I said I don't want to deal with this nitty-gritty of instruction encoding. What I really want is just a list of the RV32I base instructions. And there we have it. And this is the list that we're going to be operating off of for the rest of the class. And there is our first assembly instruction that we've collected. Give yourself a pretty little star. Add I is the first of 40 assembly instructions from the base instruction set that we'll be collecting throughout this class. Now I have an alternative way that I'm going to display this where I keep track of the pseudo instructions because that previous diagram was only the actual baseline instructions. So we have our sneaky pseudo instructions which start off yellow, end up green because they're actually lizards behind the scenes. So NOP is actually an add I behind the scenes. It's presenting as a NOP, but it's actually just an add immediate, the 0 immediate. So this is how we're going to be representing and building ourselves up a nice diagram like this. This is where we're going. This is all the stuff we're going to learn. This is madness. This is a RISC-V assembly class. But actually this is not madness because it is actually much simpler than it looks. All of that stuff is really just adds and subtracts. All of that stuff is really just loads and stores. We've got some control flow instructions over here. We've got shift instructions over here. It's a big block of shifts. We've got Boolean logic. We've got this set if, these things that say if something is true, less than, greater than, then set a register to 1. And then we've got some miscellaneous. So you can see this all, yes, there's many different variations of adds and subs and compressed versions and pseudo instruction versions, but really it's just add and subtract. You understand add and subtract, right? So not a big deal. And this is where we are currently in our journey.